Welcome back, everybody. Fair warning, this video this one might get just a little bit long. And so buckle up, in for the long haul. You see Lucy back over my shoulder over here. She's in for the long haul. Lucy, you comfortable? You comfortable? You good? Got a long example. Okay. You look out the window, go chase the birds. She's good. Don't worry about her. This is labeled 797, but it's probably not 797, whatever the current edition. At some point, I got tired of changing problem numbers. All right, Lucy, go have fun. You'll probably find a problem like this. It'll say something like air flows steadily through an adiabatic nozzle with an inlet pressure 60 psi, an inlet temperature of 540 Fahrenheit. Um, and it enters at a steady speed of 200 feet per second. It's going to exit at 12 psia, so slight vacuum, slightly less than atmospheric pressure. Atmospheric is about 14.7, give or take, it's a standard situation. And the problem is going to say, assuming variable specific heat and assuming reversible situation. So maybe it's going to ask for the maximum exit velocity, or it may just say, assume reversible. It wants us to find the exit velocity. Okay. This problem's actually pretty in-depth. It's going to take us some time to work our way through this one. Right? So, like I said, buckle up. And the other thing, we've not talked about variable specific heat yet. We're going to assume reversible, but we're not going to assume variable specific heat yet. Right? We'll come back and look at this using variable specific heat, but let's work this one using constant specific heat first. So let's record the givens here. I'm going to try to keep this video short, so if you want to pause and record the givens here, I'm going to do the same. So I'm going to pause, record. All right, let's see how you did. That's what I've got. Air, adiabatic, so Q is 0, pressure in and out, temperature in, speed in, Sgen is 0, meaning it's reversible, and find the exit velocity. Okay, so if you're good there, that means I can stop sharing. We'll work off the document camera from here, and we'll just work until we get done. Okay. So here's where I would say, all right, what's a good tool, law, equation, relationship that we might use to try to find V2? And somebody might say, well, we could use the conservation of mass, the m dot equation. Yes, we could use m dot, although I don't know the areas here. To find the speed, I would need to know the areas and or the mass flow rate. I don't know either of those. So not gonna be able. I could write down the mass flow rate equation and the conservation of mass. I don't think it's going to help us here. So what else do I need? What else can I use? Well, remember the first law does contain kinetic energy. Kinetic energy is based off the speed. So I might have enough information to write a first law equation. This is a nozzle, insulated, mass coming in, mass going out. It's control volume, steady flow control volume. No heat transfer, nothing doing work. Does not appear to be anything doing work. So E dot mass in minus E dot mass out will be 0. In minus that equals change. It's one inlet, one outlet, so it's common m dot. There's going to be an enthalpy change. So H1 minus H2, in minus out. And because it's a nozzle, there is a kinetic energy change we have to account for. V1 squared minus V2 squared, both over 2. That sum will be 0. Okay. Now let's figure out, what do we know, what do we not know? Okay, well, I don't know m dot. And I don't see a clear path to find it yet. Like, as we said earlier, if you write out the m dot equation, m dot is AV over specific volume, or rho AV. I don't know the area. I do know V1, but I don't know the area. And I'm not going to be able to find that. So I'm not going to be able to find m dot using the m dot equation. Okay, well, let's come back to m dot. We'll figure out what to do with that in a second. Let's look at the other terms. I'm looking for V2. So I'm okay with that being unknown. I do know V1, that's given. That's really high, but I think it's okay. This is a made-up problem, and honestly, that's a very, very high temperature anyway. It's not like that's room temperature. 540 Fahrenheit. If you think in Celsius, that's I don't know, 300 Celsius, maybe somewhere in that ballpark. It's high. Um, Okay, enthalpy values. How do we find enthalpy? Well, it's a property, so I got to go through the rules for my substance. What is my substance? My substance is air. That's an ideal gas. So as long as I know temperatures, I know enthalpy values. Well, I know one temperature, so I should be able to quantify H1, but I don't know the second enthalpy value because I don't know T2. So enthalpy 2 is unknown, V2 is unknown, and m dot is unknown. I might be able to get to H2, but I don't really have a good way to get to m dot. So what do we do with that? Well, if you've been hanging out or you followed along, maybe you remember that when in doubt, just divide everything by mass and see what comes out. What happens? Can you solve it by dividing everything by mass? Right? So if I just move m dot to the other side of the equation, then I get 0 divided by m dot, and m dot, I think it's safe to assume, is not 0. So I'm not blowing up the world and getting infinity there. Safe to say it just goes away. So I think I'm okay working the problem per unit mass. That's a common thing we can try. You can always try that and see if you can get to a solution. Mhm. Okay. It especially if all I have is mass in, mass out, then that's a really easy thing I can do. It's just divide everything by m dot, and then there's no heat or work that has to be divided by m dot that we have to work out on a per unit mass basis. So not a problem here. So now I'm down to V2, which is what I'm looking for, and I need to know H2 somehow. So somehow I need to be able to figure out T2 to get H2. All right. Well, how could we find T2 so I could find H2? And somebody might say, well, it's air, it's an ideal gas. Could I use ideal gas law? I might could, but I don't know specific volumes here. I don't know specific volumes. And I also don't know areas. If I knew areas or maybe the ratio of areas, I could maybe use the m dot expression to find that specific volume or the ratio of specific volumes. I can find the specific volume of state one. Notice I got P1, T1. So PV is equal to RT. So I know P1 and T1, and I can go look up R so I could find specific volume at state one. But I don't know T2 or specific volume at state two. I would need to know one to find the other. Okay. So ideal gas law is not going to help me. If only there was another tool or law or expression that we had just learned about, then maybe we could employ in a situation like this to help us find another unknown. Oh, right. That's the whole purpose of this chapter, is the second law. So if I'm working this per unit mass, let's look at the per unit mass version of the second law. That's little s2 minus little s1 is equal to the integral of d little q over t plus little s gen. All these are per unit mass. Okay. Well, let's look at this. What can I do with this? Well, what do I know about the heat transfer? I would pause and say, okay, well, what do I know about the heat transfer? And I would maybe kind of motion towards the givens and say, what do I know about the heat transfer? And hopefully somebody would say, well, it's adiabatic. Right. And I like to say, if I add up a whole bunch of zeros, which is what I do with an integral, I still get 0. And they've already told me to assume that it's reversible. Maybe they've told me find the maximum exit velocity for this nozzle or something like that. Somehow they've given me enough information in the problem statement to know that I can assume that it's not generating entropy. So it's isentropic. It's adiabatic and reversible. I have to have both of those for it to be isentropic. S2 minus S1 is equal to 0. Okay, what the heck are we trying to do again? All right, we're looking for V2, right? What the heck are we looking for? Looking for V2. Okay, how does this help us? Well, I need H2. Ultimately, I need H2, right? Or I need T2 to get H2. Now, what I know is the entropy doesn't change. And I know entropy is a property of the substance. And I have to say, okay, well, what is the substance? Well, it's air. Okay, well, can I do something with the entropy of an ideal gas like air? Yes, actually, I've got Gibbs equation. Right? And normally I'd have on the board, because I've already written it out for like review for the day or something, I might have Gibbs equation already on the board, and I could say, okay, which of these should I use? And either one's fine, because there's like we derived a couple of different versions. One has the ratio of specific volumes, which I don't know, and the other has the ratio of pressures, which I do know. Right? So I do know the ratio of pressure, so I'd probably use the version of Gibbs equation. So I could say this 0 is approximately equal to C sub P at the average temperature times the natural log of T2 over T1 minus R times the natural log of the ratio of pressures P2 over P1. Well, I know T1. I know the pressures. I know I can go look up R. I should be able to look up C sub P, right? And that would leave T2 as my unknown. All right, well, let's solve T2 out, right? So how do I solve T2 out? Well, let's move this to the other side of the equation. Let's move the minus RLN to the other side of the equation. So it's C sub P average, natural log, T2 over T1 is equal to R times the natural log of P2 over P1. And I'm going to solve for T2. So let's move C sub P over. So that's the natural log T2 over T1 is equal to R over C sub P average times the natural log of P2 over P1. And then what I can do is I can say, well, if I take e to the power, if you remember your logarithmic algebra, you don't necessarily have to do this in as much detail. But if I say I take e to the natural log of T2 over T1, well, that's just equal to e to the natural log, e to the power of natural log of x is just equal to x. So this becomes T2 over T1, right? So if I raise this side of the equation e to the power of this side of the equation, then I've got to take e to the power of this side of the equation. I got to do the same thing to both sides of the equation. Not quite enough room to do that on this sheet. I probably could have got it done, but I'm just going to go to the next sheet. This is lecture 19. We've already done 3 pages for lecture 19 because we did another example problem earlier. So it's page 4. All right, so again, I'm going to take e to the power of this side of the equation is equal to e to the power of this side of the equation, and e to the power of this side of the equation just becomes this. So I'm going to say that T2 is equal to T1 times e to the power of some stuff being R over C sub P average times the natural log of P2 over P1. Okay. Cool. Properties. Let's go get properties. Right? So the R value, all I need to know is air. Knowing air gives me the R value. I can go look that up. Easy enough. C sub P, I need to know a few things. So I need to know the average temperature and the fact that it's air. That will give me C sub P at the average temperature. Now, to know the average temperature, I need to know T1 and I need to know T2. Do we see the problem here? The heck are we trying to do, Steve? All right, we're trying to find V2. How do I get V2? Well, I'm going to use the first law. V2 and H2 are my unknowns. How do I find H2? To find H2, I need to know T2 because I don't know T2. It's air. H is going to be a function of T2. So I don't know T2. So I said, hey, let's use the second law. Maybe the second law will help us find T2. And we said, well, you know what? If I solve the second law all the way down for T2, I should be able to look everything else and I know everything else, but I don't have this guy, right? How do I get this guy? Well, I have to know the average temperature. How do I know the average temperature? I have to know both temperatures. I don't know both temperatures. Yeesh. But this is what we call a guess and check scenario. This is what we call a guess and check scenario. I need another equation. I kind of have an equation for C sub P as a function of temperature, but what I have here, I actually have a chart. This is table A2B. This tells us how C sub P changes as temperature changes for an ideal gas, in this case, air. So I'm basically going to use this chart as an equation. I don't know how C sub P changes as T2 changes, because if you look here, basically I've got one equation with 2 unknowns. I don't know T2, and therefore I don't know C sub P average. So I've got one equation with 2 unknowns, but what I have in front of you is a way to relate C sub P average to the average temperature, and the average temperature is based off of T2. So I'm going to have to guess and check. This is what we call an iterative process. I'm going to have to guess and check this one, right? So I'm going to have to guess T2. If I guess T2, that's going to give me T average. With a T average, then I can find C sub P average. And I can plug C sub P average into this equation, and that's going to give me a better value for T2. And then I'm going to repeat until I keep getting the same number over and over and over again. I'm going to take the better value for T2 that I calculate from this equation, plug it back into the loop. Yeah, it gives me a better value for T average, which gives me a better value for C sub P average, which gives me a better value for T2. And what you're going to find is you're only going to have to go through this loop once or twice. The first time through, you're going to get a really good value for T2. The second time through, you're going to basically settle into an answer almost always. At most, you'll go 3 times. If you look at this like, Steve, this is crazy. I've never seen anything like this. Well, I don't know what to tell you. When you get to fluid mechanics and heat transfer, this iterative processes, we do this all the time. We do guess and check all the time. Or at least we program a computer to do it for us. One of the two. We either do it by hand or we program a computer to do it. You're not going to be able to program a computer to do it unless you understand how the process works. This is a wonderful place to learn the mechanics of how this works. And I've just learned over the years to draw myself a roadmap because inevitably I'm going to get lost. So if I've got a nice roadmap, it says, what the heck am I looking for? Oh, yeah, somewhere along here, right? So we're going to go through this. Okay, this is a nozzle. Kinetic energy increases, which means basically the enthalpy is going to decrease, meaning the temperature is going to decrease. I'm starting out here at 540 Fahrenheit at T1. And I'm starting at 540 Fahrenheit for T1. I'm going to probably go lower than that. There's no bad first guess on one of these, by the way. Students will ask me sometimes, hey, Steve, what should I guess for T2? Well, there's no bad first guess. I need to be sharing. I apologize. Why do I say there's no bad guess? No matter what you guess, notice the first digit of C sub P is going to be 0.2. Always. The first digit is always right. The next digit is going to be very close because it doesn't change much, right? So we started at 540 Fahrenheit for T1. I'm going to say, you know what, let's guess. Let's say if T2, I'm going to keep this easy. Let's say T2 is equal to, I don't know, 460 degrees Fahrenheit. And since T1 is 540 degrees Fahrenheit, that means T average, the average between those is going to be 500 degrees Fahrenheit, which means C sub P average, based on our chart here, is going to be 0.248 BTUs per pound mass Rankine. Now, while I'm here, I'm going to go ahead and get my R value. That's just a few tables up. So I'm going to go up to table A1 and get my R value. Notice in the English units, your R value has 2 different unit sets. There are 2 values for R here for air. They're both correct. Notice the units. So if I'm plugging this R value into the ideal gas law, I'm probably going to use this one that is PSI a cubic feet. But since I'm dividing it by this C sub P value that has units of BTUs per pound mass Rankine, I'm going to use the R value that has units of BTUs per pound mass Rankine. That is 0.06855 units there of BTU per pound mass, also per Rankine. Okay. Now we're going to come back to this table in just a minute. Let's go back full screen here. Okay. What are we going to do now? We are going to plug this C sub P average value in here to get T2. T2 is going to equal T1. What is T1 again? And I'll wait, and somebody might say, well, it's 540. And I'll say, yeah, okay, so what is T1? And I'll wait, because it's not 540. That is an incorrect value. It is 540 degrees Fahrenheit, but I can't use that. I can't use Fahrenheit here. I'm multiplying by a temperature. I have to use Rankine. So how to get to Rankine? Well, I add 460 to it. That's 1,000 Rankines. 540 plus 460 gets me to 1,000 Rankines. So T1 is actually 1,000 Rankines. T1 is 1,000 Rankines. T1 times e to the power of stuff. So this is times e to the power of R over C sub P. So we've just agreed that R is 0.06855. That is BTUs per pound mass Rankine. I'm going to scribble that in there very small. Divided by, that is our R value. We're going to try this as our C sub P, 0.248 BTU per pound mass Rankine. So that ratio times the natural log of this ratio of pressures. Natural log. Pressure 2 was 12. Pressure 1 was 60. They're both PSI, pounds per square inch absolute. Now, if you've got a nice calculator that lets you do multiple lines, like a graphing calculator or something like that, that might be advantageous to you here. Because what we're going to do is we're going to go back through this loop with a different value of C sub P. So the only thing that's going to change in this equation is one value. So if I can type this all out in one line and just go back and recall and change this one value, then this actually goes pretty easy. But it's not too bad. And if I just do it in my scientific calculator, right? So that's this guy. Multiplied by, it's okay that it's negative, it just means it's going to decrease. Multiplied by, Facebook notification, silly. This ratio, well, so multiply it by 0.06855 and divided by 0.248 equals, and then I'm going to take e to that power, which is shift e to this power. And I'll multiply that by 1,000. T2, 641 Rankines. Which, by the way, if I minus 460 off that, that is about 181 degrees Fahrenheit. All right, are we done? No, because we initially said, well, what if T2 is 460? What then? And we found, well, actually a better guess for T2 is 181. That's a huge change. What does that mean? That means we need to go back through one more time, at least once more. Let's try it another time. If T2 then is actually equal to this better guess of 181 degrees Fahrenheit, and again, T1 is 540 degrees Fahrenheit, so that means T average 181 plus 540 divided by 2. T average is about 360.5 degrees Fahrenheit, which means C sub P average is equal to, and again, what am I doing? I'm going through this loop again, right? I went through it once, started with a terrible guess for T2. That gave me a better guess for T2. Now I'm starting back over with this guess for T2. And I'm going to go through the loop again. And that's going to give me a better value now for what C sub P average should be. So at about 360, I'm going to be between 0.243 and 245. So you could interpolate to the fourth significant figure there. To 3 significant figures, you don't necessarily have to interpolate that here. And that's the best we're going to get is 3 significant figures. So between 300 and 400 degrees Fahrenheit, the best you're going to get is 0.244 BTUs per pound mass Rankine for C sub P average. Again, you are more than welcome to interpolate that fourth significant figure. In the interest of time and keeping this video a little bit short, I'm not going to, right? And so then again, I'm just going to recalculate this equation, but instead of 0.248 that we used last time, I'm going to use now 0.244. You're welcome to pause and run these numbers with me. I'm going to pause recording and then I'm going to go ahead and run these numbers out because you've already seen me shuffle these through my calculator once. All right, I've got my number. You got yours? Here we go. It means T2 is about 636 Rankine or about 176 Fahrenheit. And if you run back through with this now as T2, and we say, well, T2, if T2 is 176 and T1 is 540, then the average is going to be about 350 something, which means C sub P average is still going to be 0.244, and we're going to recalculate it. We're going to get the same number again. And that's how you know you're done with the loop, is when you keep going through the loop and you keep getting the same number over and over again. I plug this value in, run through, I get this value. If I plug this value back in, run through, I would get this value again every time because this number is not going to change, right? I've zeroed in. This is the actual number for C sub P, meaning this is the number for T2. Right. Okay, are we done? What the heck, Steve? No, we're not done. Unfortunately, we're not done. What are we looking for? It's back up at the very beginning. We're looking for V2. All right, I got to find V2. What do I need to find V2? Well, I'm going to use this. I didn't know H2, but I now know both temperatures, which means I can quantify delta H. So I can either go look up H1 and H2 from properties, right? Or I can also use specific heat, which I now have settled on a value for specific heat. So V2, if you solve out the first law equation, is going to be the square root of 2 times H1 minus H2 plus V1 squared over 2. You're welcome to solve the first law equation. I just showed it to you. And you'll get here. You can approximate this as the square root of 2 times C sub P at the average temperature, which we now know, times T1 minus T2 plus V1 squared over 2. Oh, close quantity. C sub P at 2 times that whole quantity. Okay. V2 then is going to equal square root, and now we can start plugging things in. Square root is going to be 2 times quantity. I'm going to have C sub P, we've agreed, is 0.244 BTU per pound mass Rankine. Multiply by the temperature change. I'm going to do brackets out here. Do brackets. Multiply by the temperature change. T1 is 1,000 Rankine or 540 Fahrenheit, whichever one you like. T2, we've settled on a value of 636. Those are both Rankines. Now, here's where I like to ask the question, what units would you like? What units make sense? Does the square root of BTUs per pound mass, does that mean anything? No, that does not. So what units would you like? Well, you'd actually want feet squared per second squared. And so if you go look up in conversion factors, you'll find that there's about 25,037, if memory serves, feet squared per second squared for every BTU per pound mass. Anytime you're adding enthalpy to kinetic energy or combining enthalpy with kinetic energy, you're going to have a units issue. Same thing in the unit system. It's just a factor of 1,000. Here it's a factor of 25,000. But yeah, there's 25,000 and something. I think it's 37 feet squared per second squared per BTU per pound mass. And that will leave us then with feet squared per second squared for this whole quantity. Because I need to add that to then V1, which was, if I look back in my previous notes, that's going to be 200 feet per second. That's going to get squared and divided by 2. And the whole thing's going to get multiplied by 2. And then the whole thing's going to get square rooted. I'm going to pause because this video is getting really long and let you run the numbers. So I'm going to run the numbers. All right, how'd you do? Here's what I got. It's a ridiculously big number. 2118 units there are feet per second because this is feet squared per second squared and this is feet squared per second squared, and we're taking the square root, so it's feet per second. Is that a realistic number? I don't know. Probably not, although we are at very high temperatures. So the speed of sound is higher as you increase temperature, but I don't know if this is realistic. But it's based, in order to satisfy the conservation of energy principle and to be isentropic, This value is what makes sense. Whew. Okay, I'm going to stop here, and we'll do lecture 20, and we'll go from there.